In this tutorial, we will show you how to set up and use our dynamic reverb system. First of all, in your character blueprint or in C++, attach a dynamic reverb component. This component will continuously scan the scene around the player and calculate the parameters used in our reverb system. If you enable these debug features, you will see how the traces are done. By default, we scan the scene 30 times per second. Each scan consists of 8 async line traces in 8 random directions. The reverb parameters are updated based on the hit results. This has very minimal impact on your games. If your character movement is very fast, for example, when driving cars, you should reduce the trace tick and the number of interpolating frames. We set the trace channel to cover here, but you should use a custom channel for better reverb controls. To pass all the calculated parameters from this component to MetaSounds automatically, we created a custom interface for MetaSounds. You will see it when you add a new interface to your graph. We call it modal spatial. When you add this, you will see all these parameters. They are automatically fed by reading from the closest dynamic reverb component. But to use this interface, you will need to enable it in your project settings platform section. For example, on Windows, you must set the source data override plugin to modal spatial. Then you must have a sound attenuation settings file. You can find one inside the attenuation folder. Make sure that you enable source override in your attenuation settings. Finally, inside your graph, you must reference it here. By doing that, our plugin will automatically read the parameters from our dynamic reverb component and fed the data to all graphs that implement modal spatial interface. Now, you can start using the dynamic reverb HRTF node. You will need to connect all the interface inputs and the input audio with its trigger events. Let's test it with some different room sizes and distances. So what this node does is that it will do all the spatialization for your audio. This includes head-related transfer function, distance attenuation, air absorption, and reverb. If you want the reverb to be more obvious, I recommend increasing the delay to 0.03 second. You should never delay more than 0.1 second unless you know what you're doing. Also, gain wet is the reverb gain. You can increase it to 1. And now you will hear more reverb. At a far distance, you will hear more reverb than the dry audio. Other important inputs are the number of modals in each band. We set these to high values, so by default, this node works on any kinds of SFX and music. You can reduce the computational costs by reducing the number of modals, but this will also increase the metallic artifact at the reverb output. To reduce this unwanted metallic effect while keeping the same number of modals, you can increase the frequency scatter scale. Don't increase it too high, or else the final results will become a chaotic mess. For music, you might want to reduce the frequency scatter scale to 0.02. Finally, if update room params is false, the reverb node will only update its parameters on play, which is good to avoid making your reverb effect feel like it follows the player. You should enable this if your graph is attached to a movie object. For example, a car engine SFX. Before I go into this node, I want to mention this enable HRTF a bit. It's a float here because MetaSounds interface only allows float variables. This is linked to the enable HRTF variable in the dynamic component. As you have known, HRTF works wonderfully on headphones, but its spatial depth is poor on speakers due to crosstalk and extra ear filtering. Personally, I will keep it enabled even on speakers, so my SFX will always sound the same. But you might want to allow players to disable it on their own. So we provide this variable. When it's disabled, our HRTF node will switch to stereo panning with equal PAL law. Okay, let's take a quick look inside this node. You can see that the input audio is passed into our reverb node. Then both the reverb and input audio are mixed together before passing into our HRTF node. At the output, we mix the reverb one more time for both the left and right channels. This is not physically correct, but it's close enough. A correct implementation should have used multiple HRTF nodes to simulate reverbs from multiple directions. Something like this. Note that you must only use the audio from the reverb node. Repeat this several times. Then, you can mix all of them together with the dry signals. However, this increases CPU costs and also reducing the localization accuracy. So we just add the reverb to both ears to make them feel more surrounded. This leak is increased with distance to make it more dominant on distant sound. And because the reverb node has built-in air absorption for different frequencies. This allows us to simulate air absorption on distant sound too. So you don't have to do all that low-pass, high-shelf, and randomize EQ which costs 1 to 2% of CPU. We modeled the air absorption from real-world impulse responses, so it's also pretty accurate. Okay, if you look at this node, you will see these parameters are kept at their default values. You don't need to change the phase scatter scale. In future updates, we might remove this pin. Decay min is the minimum decay value for all frequencies in all environments. It's just a safeguard, as the calculated parameters can't reach this value. You shouldn't change decay slopes B and C, they are planned for future updates. Room size, absorption, and open room factor are controlled by our interface. They are calculated inside our dynamic reverb component. Room size might sound a little bit misleading. It is actually the room volume, but powered by 1/3. Absorption is only air absorption at the moment. Open room factor is the openness of your scene. Normally, in an open area, the reverb gain is reduced, and the wind will also modulate its duration. So this open room factor affects both the amplitude and the decay rate of our reverb. And this is how we do the whole spatialization in our plugin. But this is just a starting point. You can easily extend or customize this to suit your needs. For example, using multiple HRTF like I said earlier, or adding some EQ and filters to simulate even more air absorption. If you're an experienced sound designer, you might wonder why we don't use an effect chain and audio bus for the reverb effect. While it's true that it will improve performance and allow a higher reverb quality, it's also more limiting and harder to preview sound effects. By doing this per sound source, you can control the final results right inside the graphs. And you take less of a round trip between placing the audio into the world, playing in PIE, then revise the effect. Okay, let's start the demo to see how all of this spatialization system works. I overemphasized the reverb on footsteps a bit on this demo. Notice how the reverb lasts longer when I move to a more enclosed room. This is just a test to see how the system reacts to a more complicated scene. Okay, let's see how this works on a moving sound source. This demo is our full system with HRTF. It is full 3D spatial depth on headphones. This one is with stereo panning instead of HRDF. It is worse spatial depth on headphones, but it's fast and doesn't alter your SFX. And this one is without reverb. The gain is scaled with distance, and there is no air absorption. Spatial depth is very flat. Even at far distance, it still feels very close to the player. Reverb is a very important effect to make the sound actually exist in your scene. We also prepared a demo on Lyra. This is built on Unreal 5.4. The dynamic HRTF graph is added to all gunshots, explosions, footsteps, bullet impacts, and bullet whiz sound effects. UI, SFX, and music are kept intact. I also removed the distance attenuation filtering on gunshot graphs, because, as mentioned, this is done inside the reverb node. In the end, the new graphs actually cost less CPU than the old ones. The dynamic reverb component is added to the hero blueprint. So for each player, we have a dynamic reverb component. Basically, we have 4 components running when playing with parts. When a sound is played, the plugin will read the parameters from the closest component. Of course, in a real game, you should only spawn the component for the local player. Notice how the reverb of footsteps change based on the location. Since we can have a lot of gunshots at the same time, I toned down the reverb effect on gunshots a bit. You can download both demos in the description below. Next week, we will release the update and add a version for Unreal 5.4. There are still some areas where we want to improve, for example, reverb on faraway sound sources. So expect some dramatic changes to spatialization in future updates. Bye for now, and I'll see you again once the new features are ready.